Nice. Welcome everyone to this week's Intercontinental Seminar on Gravity and Cosmology. We have the pleasure today to have with us Theodoros Nakas. He got his PhD in 2022 at the University of Ioannina here in Greece. And then he spent a couple of years in the National Technical University of Athens, and now he's a postdoc in IBS Korea in the Daejeon. And today he's going to talk about scalar Hadron black holes from singular to regular solutions and their stability. So the floor is yours.
Thank you very much, Costa, and thank you a lot for giving me this opportunity to give the seminar. For those who don't know me, as Kostas mentioned, I'm Theodoros Nakas. I'm based in Korea right now, and I'm a postdoc researcher. So today I will be talking about scalar here in black holes, and I will focus both on singular and regular black hole solutions. And we will also discuss the axial stability of the solutions. And as we will see, the singular black hole solutions in the context that we will discuss, they have primary scalar hair, while the regular black holes have secondary scalar hair. But I will explain everything in the following slides. So my talk is based on these three projects. The first two are finished and they were done in collaboration with Thanasis, Christos Charmousis, Nicola Leker Panagiotta Kanti, and Nikos Hantsifotis. And the project that is still in progress is in collaboration with Sebastian, Simon, and Karim Nui. Okay, so Oh, okay. So the outline of my talk will be the following. At first, I will briefly give some motivation for Horndeski and beyond Horndeski theories. I will explain what we mean when we say that a black hole has primary or secondary scalar hair. Then I will come to our solutions that we found in the context of beyond Horndeski gravity. And finally, I will explain and discuss the axial stability of perturbations for these solutions. And I will sum up and summarize with conclusions and future directions of research. So, what do we certainly know about our universe? What we know is that the general theory of relativity and the standard model of particle physics are not sufficient to describe it. We know that although GR is very successful in describing the vast majority of astrophysical and cosmological measurements, it is not a fundamental theory of gravity. Why? Because it predicts space-time singularities. These singularities cannot be fully understood within the framework of the theory. For this, we need a quantum theory of gravity in order to understand what is happening inside the black hole and to solve the singularity problem. On top of that, quantum gravitational corrections, you know that they play a significant role in the early universe for the inflation, for the expansion of the universe, for the singularity problem also in the initial singularity. So again, quantum corrections are very important for gravity. And we still don't know what a quantum theory of gravity may look like. Moreover, the true nature of dark matter and dark energy is still completely unknown. Here, maybe we will obtain a deeper understanding from modified gravitational theories or from particle theories beyond the standard model. And finally, the hierarchy problem and the unification of gravity with the other fundamental interactions require again new physics. And here you can see some of the main paths that one could follow for new physics. On this bottom left panel, you can see theories that they are trying to quantize gravity. And everybody knows string theory, loop quantum gravity, causal dynamical triangulation, or non-commutative geometry. On the bottom right panel, we have again higher dimensional theories of gravity, which are motivated from string theory. Here we have on the top left panel, we have theories with torsion, non-metricity, Palatinic gravity, massive gravity, or Java gravity. But today I will focus on this top right panel and mainly on theories that are called Horndeski and beyond Horndeski. And the beyond Horndeski gravity is a part of, sorry, is a part of the quadratic DOST theories. DOST stands for degenerate higher order scalar tensor theories. Okay, so let me explain. But before, someone might wonder, why do we choose scalar tensor theories? Do they have anything special, this kind of theories? The short answer is no, but they are the simplest modifications of gravity, which means that we only have, on top of gravity, of the metric tensor, we have one additional scalar degree of freedom. Nothing more, very simple modification. And inside these theories, we can find Brans-Dicke theory, which is used for many cosmological models extensively. We have Horndeski gravity, beyond Horndeski, and DOST theories. And as you know, these theories, although they modify gravity, observationally, they still they can still satisfy the observations in in the solar system, but they can modify gravity in large scales for cosmology, for inflation, for the early universe, especially. Another appealing characteristic of scalar tensor theories is that they sometimes constitute a limit of other higher dimensional theories. A distinct such example is that if we start from a higher dimensional Lovelock theory, and if we perform a particular Kaluza-Klein reduction, what we will find effectively, if we go to the 4 dimensions, we will find Horndeski gravity. Finally, I cannot, I should mention, I should mention that string theory also predicts that the actual theory of gravity is a scalar tensor theory. Why? Because in the setup of string theory, the graviton is always accompanied by a spin zero partner, which is the dilaton. Therefore, we can safely say that scalar tensor theories are the simplest well-motivated departures from general relativity. And how can we construct healthy extensions of GR? What is the criterion to write down a scalar tensor theory? The criterion, the most important criterion that we have is that we should satisfy the we should have a theory that does not contain Ostrogradsky instabilities. What is this? This is basically ghost instabilities that they can appear in the equations of motion and in the Hamiltonian analysis, basically. So the Ostrogradsky theorem states that a system described by non-degenerate higher derivative Lagrangian suffers from ghost-like instabilities. And the word here, non-degenerate, is very important because we will see later that if we go to degenerate theories, then we can evade this theorem. Let me give you a simple example from classical mechanics. So let's say that we have this Lagrangian. We have double dot here. So if we compute the Euler-Lagrange equations, we find this equation for the scalar field. Please, you can interrupt me whenever you like. You don't have uh, to remember what you wanted to ask. You can interrupt me and you can ask whatever you like. So from this Lagrangian, the equation that we have that we obtain is of this type, and we have four uh, fourth a fourth derivative in time, as you can see. This means because we have a fourth derivative uh, for the scalar field or the coordinate basically here, we need four initial conditions, which indicates that this Lagrangian contains two dynamical degrees of freedom. And how can we see this? We can see this by using some auxiliary variables, psi, for example, here, and then we perform a field redefinition in the Lagrangian. And finally, one can verify that this Lagrangian, the initial Lagrangian, takes this form. And you see clearly here that we have two dynamical degrees of freedom. We have this small q here and the capital Q. And you notice on top of that, that independently of the sign of the parameter A, there will always be one of the two fields will play the role of a ghost field. Because whatever we do, there will always be a minus sign, the wrong sign in front of the kinetic term of one of the two scalar fields. Therefore, we see, this is a simple example that shows that if we have a non-degenerate higher derivative Lagrangian, then we always have ghost-like instabilities. So how can we, what is the most general scalar tensor theory that we can write down that is devoid of Ostrogradsky instabilities and leads to second-order equations of motion? This theory is called Horndeski gravity or Horndeski theory and was formulated by Gregory Horndeski in 1974. And you see here that we have four different Lagrangian densities, and you see that we have higher order derivatives of the scalar field, but because this theory is internally degenerate, the terms, when we evaluate the equations of motion, these terms will cancel higher derivatives, and we will obtain a healthy scalar tensor theory with second order equations of motion, which is healthy and does not contain Ostrogradsky instabilities. But people, after many years after the formulation of Horndeski gravity, they realized that we can even go beyond this theory. And how can we go beyond? We can go beyond by performing these formal transformations. Not only in this way, I will come to this a bit later, but the first way that people realized that we can find new scalar tensor theories was through disformal transformations. And what is a disformal transformation? Is a transformation of the metric in this way. So we have the scalar field from the original theory that we started from. We have the kinetic term, x is the kinetic term of the scalar field, and we have the initial metric. And this is a generalization of conformal transformation. And it's this formal because we have, of course, this term here, the second term here. And you see, for example, you see this diagram that we have a small, so the traditional scalar tensor theories that we usually meet in cosmology, which is basically like a Brans-Dicke theory, is a small portion of Horndeski, gravity. Then we have beyond Horndeski, and we have DOST theories and theories with extra degrees of freedom, of course. And DOST, degenerate higher order scalar tensor theories can be even larger as a group of theories, even compared to beyond Horndeski gravities, because there you impose by hand degeneracy conditions to kill the ghostly instabilities, the ghost-like instabilities, and you can play this game on and on and on. If you want, you can continue playing this game up to whatever order of derivative you like. But you have always to add degeneracy conditions uh, to kill the ghost instabilities. Okay, and so here you see that starting from a Horndeski theory, if we apply a transformation of the form C of phi and D of phi, then this kind of transformation does not allow us to go to beyond Horndeski. This transformation will leave us inside Horndeski theory, but with a different form of the scalar field. In order to go to beyond Horndeski, we have to make a transformation of this form, d of x, where x, I remind you, is the kinetic term of the scalar field. If we have such a transformation, then we find a theory with new terms on top of the Horndeski terms. And in this case, we have additionally these two terms, L4 beyond Horndeski and L5 beyond Horndeski. Okay. Is there any question up to this point? Okay. Okay. So let me now move to black holes. So you know that in general relativity, black holes are characterized by three observable quantities, or hairs, as we often we often say. This is the mass of the black hole, the angular momentum of the black hole, and if we include electromagnetic, the electromagnetic term in the action, we will also have the electric charge in the black hole. But without this electromagnetic term in the action, a black hole is characterized by the mass in the angular momentum. And in the context of GR, there are uniqueness theorems and no scalar hair theorems that say and prove that we cannot have more than this. A black hole cannot have additional uh, information or additional hair, if you like, besides the mass, the angular momentum, or electric charge. However, if we study and if we go to scalar tensor theories or in general theories beyond GR, then we can have and we can evade these kind of theorems. The no scalar hair theorems, there is always a way in particular setups that we can evade these theorems. We can evade these theorems with in Einstein's scalar Gauss-Bonnet theory, which is basically a Horndeski gravity. and we can evade these theorems also in beyond Horndeski theories. And let me now explain. And of course, once we evade these theorems, we find new black hole solutions that have different characteristics from the GR black hole solutions. And in that sense, we say that we have generated hair to the black hole. If it is a scalar tensor theory, then the hair will be of scalar nature. If it is another type of theory, then of course the hair will be of another type. But here I will focus only on scalar tensor theories, and the hair will be of scalar nature. Okay. And now there are two different cases. We have a scalar tensor theory, and we find a solution for the metric and for the profile of the scalar field. Of course, because we have a non-GR theory, the metric solution, the solution of the compact object, will be different from the metric of a black hole, of a GR black hole. In that case, if we only have, in the case that we only have one free parameter for the compact object, for the solution, which this parameter will always be associated with the ADM mass of the object, then because we don't have a new parameter, a new information inside the metric, we say that this is secondary here. Because although that we have a scalar tensor theory, we have a modified solution, yes, but we don't have new information, a new parameter appearing inside the metric of the compact object, describing the compact object. But in the case that we have a new free independent parameter inside the solution, then we say that we have primary here, primary scalar here, because this is exactly related one to one, if you want, correspondence with the existence of the scalar field. That's why we say that in this case we have primary scalar here. Okay. Let me first, before I go to our results, let me first give you a simple example of a black hole solution in a simple scalar tensor theory. So this is the Bokharov, Abronikov, Melenkov, and Bekenstein solution back in the 70s, and you see here that we have the Einstein-Hilbert term, we have the kinetic term of the scalar field, but we also have a non-minimal coupling between the scalar field and the gravity and gravity, the Ricci scalar. If we solve the equations of motion, we find that from this theory we obtain an extremal Reissner-Nordstrom black hole. Why? Because this is exactly, if in the case of Reissner-Nordstrom, which is charged black hole, in case where Q is equals M, we obtain this exact solution. But in this case, we only have extremal black hole solutions. And the profile of the scalar field is the scalar field that you see here from this relation. What do you notice? You notice here that both in the metric and in the profile of the scalar field, we have only one free parameter. And this free parameter is the ADM mass, the parameter M. So, from what we said earlier, this solution describes a black hole with secondary scalar hair. So let me now move on to what we did in order to find black holes with primary scalar hair. So we focused on the shift-symmetric and the Z2 symmetric part of the beyond Horndeski theory. So what we have from the full theory, we only have the G2 term, G4, and F4 term. And you notice that the whole theory contains only derivatives of the scalar field phi. That's why it is shift symmetric. X here, as before, is the kinetic term of the scalar field. And because of this symmetry, of this shift symmetry, we can allow this linear time dependence inside the expression of the scalar field. And even if we allow this linear time dependence on top of the radial dependence, we still find static, spherically symmetric, and asymptotically flat solutions. Because when we go, when one uh, calculates the equations of motion from this theory, you always have derivatives for the scalar field. You will never have the scalar field to appear by its own. Therefore, from the equations of motion, it is guaranteed that the solution will always be static, even though we have this linear dependence, time dependence. So, to find static, spherically symmetric, black and asymptotically flat black hole solutions, we made also this general assumption for the metric, for the line element, which is the most general answers that you can have. And now, what is very important is that this parameter q here is exactly related to a scalar charge that emanates from the nether current, from a nether current which originates from the internal shift symmetry of the theory. So we have shift symmetry. This shift symmetry of our theory generates a nether current, which by its turn gives rise to a scalar charge. And it's scalar charge because we have only a scalar field on top of gravity. We don't have anything else. It cannot be anything else. And if you make the computation, this scalar charge is always proportional to a power of this q parameter, as we will see in the examples that I have for later. So, and now we want to solve in the most general way the equations of motion. Here, for the equations of motion, we used this auxiliary function z. And we have these three equations. So, for the first one, how can we solve very easily the first equation? What we have to assume is that the black hole is homogeneous, as we say. What does it mean? Homogeneous, that h here and the metric function h and the metric function f, they are the same, as it is in the Reisner-Nordstrom case, the Schwarzschild case, in GR. So, for homogeneous solutions, the first equation, it has a solution which is z equals to gamma. Gamma is just a coupling constant, a constant here. For the second equation, since z now is just a constant, basically this z here is redundant. It's just a constant. We don't need z here. So we have g2x, and g2x means derivative in terms of x, of the model function g2. And here g for x also is derivative with respect to x. Here, to solve this second equation, we can make this assumption that the model function g2 is linearly dependent of the model function, g4 is linearly dependent on the model function g2. And if we make this assumption, we can algebraically solve equation 2 for x. And we find the radial dependence of x, of the kinetic term of the scalar field, for all these models. Because here we don't have a specific model. We have a general family. We have a family of models because we have not yet specified a particular G2 for our theory. we can have whatever G2 here, but the kinetic term of the scalar field will always have the same profile. And finally, substituting everything in the final equation, we find the general expression for the metric function h, which of course h equals to f because we have a homogeneous solution. And now we make a general assumption for G2, basically in this way. S is just an integer, and this function can describe any analytic function, also square roots. We can describe almost any function that you can think of. And the general solution is this. And you see here that we have a hypergeometric function. Because we are interested in asymptotically flat solution, we take the expansion at infinity. And we immediately notice, in order to have asymptotically flat solutions, we need to kill this term, and we also need to make this gamma, the argument of the gamma function, to be well behaved. So what we need to assume? We need to assume that C naught is 0. C naught, from here you can see that C naught plays the role of the cosmological constant. So we don't put a cosmological constant in our theory, basically. This is what we are saying here. And then we fix zeta in terms of gamma, and we fix it to unity. And also, we need to impose that n over s will always be greater than 3 over 2. Okay, so let's see the first concrete example. So here, we keep only in G2, we keep only the C2 term, the C2 contribution, and we kill any other contribution for of the power of x, of the kinetic term. And we have this, and we find these model functions. This is the G2, this is the G4, and this is the F4. Eta and lambda are coupling constants of the theory. And now you see the solution, the black hole solution that we have. So we have a homogeneous spacetime, as we said previously, but now you see that we have the first and second term, but we also have this third term, which is the correction from the Schwarzschild geometry. Because if we set q equal to 0, then what we have? We have the GR limit, and we have a Schwarzschild solution, basically. We have nothing, no modification for q equal to 0. So we have a continuous GR limit, but in the case that q is not 0, we have primary scalar here. Why? Because we have a new independent free parameter, which on top of the mass, which is the ADM mass, we have the parameter q. Something that we didn't have in the case of BBMB solution. Okay. And now,
Question.
yes, please. Yes, please.
You have this black hole solution. Does it have a horizon, and do you know what is the causal structure of the solution?
Yes. Yes, I will come to this in the following slide. Yes.
Okay. Okay. Thank you.
Yes. So now from this solution, we can, and from the theory, of course, we have everything. We have the form of the kinetic term, and we have also the expression for the nether current. And we can calculate the scalar charge. And you see, as I already mentioned, that the scalar charge is related to this parameter q. Coupling constants of the theory, but q is a free parameter. And as I already said, for q equals 0, we have the GR limit and the Schwarzschild solution. So let's see now how this, what kind of solutions we can have here. So asymptotically, this this function here is of this form. So we have 1 minus 2m over r, which is Schwarzschild solution, and we have a correction, the next correction is 1 over r squared, which is the same correction that we have from the Reisner-Nordstrom, in the Reisner-Nordstrom black hole. But here, the Q is not of electric nature, but is of scalar nature, and is a free parameter. So here, in this case, and of course, we can play with the coupling constants. We can have negative coupling constant or positive coupling constant. And you can see from these two figures, for example, on the left figure, for eta negative, we have black hole solutions with one horizon, which for fixed mass, their horizon is larger than the Schwarzschild horizon. Because you see, we keep the mass m, the parameter m, the same, and we change q. And the horizon becomes larger. So for the same mass, we have a larger black hole, basically. In the case where eta is positive, we can have solutions even with three horizons, as you can see here. We have one root, 2, and 3. We can have up to 3 roots for the metric function f. And of course, if we increase q a lot, we can have also naked singularities, which is the same story as in the Reisner-Nordstrom solution. But of course, we don't expect that these solutions are physical solutions. But here, we have something else which is very interesting. If we take the expansion close to the singularity, what you notice here is that we have 1 minus this term, which is 1 over r, and then all the rest terms are r squared, r to the 4, even powers of r. So, in order to get rid of the singularity, we need to make this term to vanish. Can we do this? Of course we can. Why? Because we have two independent free parameters to play. We have the mass of the black hole and we have Q. Of course, eta and lambda are also constants, but they are fixed constants. They are coupling constants of the theory, so we cannot freely play with them. These constants are fixing the theory, basically. We can only play with the mass and with the Q, the scalar here. And if we do that, we can have on top of that, or on top of these singular black hole solutions with primary scalar here, we have regular black hole solutions. And you can verify that in this case, the curvature invariants are infinitely smooth. So we have a regular black hole solution in this case. As you can see from this, on this left figure. But we can also have solitonic solutions. Solitons are basically massive objects that they have no singularity, but also they don't have a horizon. But this is not a problem because the censorship theorem says that, from Penrose, says that we cannot have a naked singularity without a horizon, but we can have another compact object without a horizon that does not have a singularity, that does not hide the singularity. So basically, we only need to hide behind horizons. We need to hide the singularities behind horizons, but we don't need to hide anything else which is regular. And this, but okay, let me mention also this. In this case, because we fixed Q in terms of the mass of the black hole, in order to kill the singularity, Now, these solutions do not have primary here. They have secondary here. Because now, the only free parameter is the mass. Because in order to maintain the regularity, the Q should change accordingly to the mass of the black hole. Okay. And I have one more example, which in my opinion is even more interesting.
Sorry,
And
may I
it's,
interrupt, Theo?
yes,
But
yes.
the previous solution also has a parameter lambda, which you can turn, right? So,
No. Lambda is from here, if you see, is a coupling constant. So basically, it's something fixed. If you give me the theory, you give me also eta and lambda. They are fixed parameters. I don't change these parameters.
okay.
I consider them fixed because they are coming from the theory. But the mass and Q are free parameters. They are results of the solutions, of the solution basically. Integrating constants, if you like.
I see. Okay.
Yeah, because even in GR, for example, if you solve GR in vacuum only with Ricci scalar, the mass of the black hole comes as an integration constant. That's why it's free parameter. And what does this mean? This means that if you give me GR, if you give me a theory, then I can have many different black hole solutions with different masses, but of the same geometry. This is why we want the mass and the scalar here to be free parameters. Because if they are parameters of the theory, then they cannot change. Basically, we have the theory and we have one object with one mass, for example, or one value for Q. It's not free, but should be free. So for the second example, instead of G2 that is x to the power of 2, now we have x to the power 5 over 2. And here we have a simpler somehow solution because we don't have arctan. We have this solution. And this solution is basically an extension of the Bardeen solution. It's singular, but it's extension of Bardeen solution because it's the singular extension of Bardeen with primary scalar here. Because we can also have the Bardeen inside of this solution. So let me explain. So here, what you see that if we take the expansion at infinity, we have again the ADM mass M, and we have a correction, but now the correction is in the order 1 over r to the cube, not r uh, to the 2. So here the correction comes later. It's a smaller correction, basically. And you see that we can have singular black holes with one or two horizons, and we can have here on the left figure, we can have one horizon, two horizons, and again, if we increase the parameter, the value of Q, we can have naked singularities. But now, once we fix Q in terms of M, in order to kill this second term here at the expansion close to the singularity, we can have again regular black hole solutions and solitonic solutions. And if we substitute Q in terms of the mass from this relation here in order to kill this term, what we find? We find this geometry. And what is this geometry? This geometry is the Bardeen solution. But now we have found this solution in the context of beyond Horndeski gravity with a free mass parameter. But we also have an extension of Bardeen the singular extension of Bardeen, which possesses primary scalar here. Because again here, because we fixed Q in terms of mass, we have secondary scalar here. Why I mention this? I mention this because there are many famous papers in the literature that they used nonlinear electrodynamics to obtain and basically to support regular black hole solutions, but because the method that was used in that were used uh, the methods that were used in these papers is basically reverse engineering. So you have a general nonlinear electrodynamic theory, and you try to force a solution of that you want. You try to force it inside the theory. You try to force the theory to support this particular solution. And this is problematic. You can make it work, but with some restrictions. What are the restrictions? The restrictions is that you make, because you make this reverse engineering, you have the problem that the mass of your black hole will appear as a coupling constant of the theory. What we discussed just before. Um, so in this case, the theory will result to a black hole, but this black hole will have always a fixed mass. Because if you try to change the mass of the black hole, you change the theory basically, because you change the coupling constant of the theory. So you cannot have Hawking radiation in this context because M is not free. You cannot have any astrophysical phenomenon that is related with black holes in this kind of setup because mass is not free. So we say that the beyond Horndeski gravity constitutes a more natural framework to describe the Bardeen solution and also other regular black hole solutions. Because let me clarify this if it's not if I was not clear, because here from this setup we can have infinite different families of solutions. You give me a G2 that satisfies these conditions, and you have immediately G4, you have F4, and you find new black hole solutions with regular counterparts. So now let me move on. Do I have time? I don't know how am I over time?
No, it's fine. I mean, 7, 10 minutes.
Okay, thank you.
One question.
Yes, please.
To make the black hole solution regular, you chose Q, right?
Yes,
So it looks M is still a parameter, arbitrary
it's free.
parameter,
Exactly,
right?
it's free. Yes,
So
of course.
I don't understand why you say that black Hawking radiation is not allowed.
In the case, sorry, maybe I was not clear enough. So,
Mm.
in the context of Bardeen, but in
Mhm.
the context, so the Bardeen solution coming from the beyond Horndeski gravity, you can
Mhm.
have Hawking radiation, you can have everything because the mass in this case is free. But
Yes.
if you start from the nonlinear electrodynamic theories
Mhm. Mhm.
and you play the game to find the Bardeen solution there with reverse engineering, there, in this case, mass is not free, is a coupling constant because
In your solution, you have a free parameter Q, which you choose to make a
yes,
solution.
yes,
So
yes.
still M still remains.
Sorry, so what still remains?
M still remains.
Exactly, exactly. No, no, no. I'm comparing. Yes, I yes. This is exactly what I'm saying. I'm comparing the Bardeen, this Bardeen solution coming from the beyond Horndeski, what we did basically, we found Bardeen from the beyond Horndeski. In the beyond Horndeski, M is free. If you try to, from this paper here, if you try to do the same, you will see that the Bardeen solution has the same profile, the same expression here, but the mass, the mass parameter M appears as a coupling constant of the theory here.
Okay, so
This
that's
is
a
the problem.
different
So
theory from yours.
yes, so this is the problem in this case. This is the problem because from the non, so for the same solution, but from different theories.
Okay, thank you.
Yes. So in this setup, it's problematic because the mass is fixed, cannot change. Otherwise, you change the theory. So yeah, I think, I believe now, is it clear or no?
Clear.
Thank you, thank you. So now let me move on to the perturbations because, of course, if we have a black hole solution, we should check the stability of the solution because if the solution is unstable, then we cannot take it seriously as an astrophysical object, for example, because it will decay or evaporate very quickly or it will never form in the universe. So, for the axial stability, for linear perturbations, we have the background, and what we do is that we have, on top of that, we have h mu nu, which is a small perturbation compared to the background, g naught mu nu. And because we have spherical symmetry, we take advantage of this symmetry. And we know that the background and the perturbation, the linear perturbation h mu nu, will decompose into the spherical part, the radial part, and the temporal part. And due to this decomposition into the temporal and radial part and the angular part, we can distinguish the parity of the perturbations. We have two different parities for the perturbations. We have the axial sector, which is odd parity, so h mu nu transforms like this, and we have the even parity modes, for example, that transform like this. And in any scalar tensor theory, and in most cases, in most theories, in most modified theories, axial perturbations are simpler compared to the polar perturbations. The axial sector is much simpler. Why? Because in the axial sector, the scalar field does not contribute. Basically, it's just a perturbation of the metric, not of the scalar field. Why? Because the scalar field transforms evenly under parity, not oddly. But in the even sector where we have both the metric and the scalar field to contribute, the equations, the resulting equations are much more difficult to be solved. And until now, in the context of Horndeski and beyond Horndeski, we don't have a clear understanding of the polar sector. We only know how to deal with the axial sector. So, I will now, from now on, I will focus only on the axial sector. So, for the axial part, we have this decomposition. So, this is the decomposition of time, this is the radial the decomposition, and this is the decomposition of in terms with respect to the angles, to the angular part. And we have two equations of motion that I schematically name here calligraphic E1 and calligraphic E2. And we have two independent metric functions in the perturbation level. So the first one will be a constraint equation because does not contain second order derivatives with respect to the radial coordinate. So one of these two will always be a constraint equation. And we can use this in order to solve H naught or H1 in terms of the other one. So basically we have only one equation, independent equation. And this equation in most cases, in scalar tensor theories at least, I cannot say this in general, but at least in scalar tensor theories, this equation can always be brought in this general form. R star here is the tortoise coordinate. What is the tortoise coordinate? We have the black hole horizon and we study perturbations outside of this object. So the radial coordinate is a transformation of the coordinates that takes the coordinate of the horizon, of the black hole horizon, and takes it to the minus infinity. So we have R star goes from minus infinity to plus infinity. Otherwise, we have R going from R horizon to plus infinity. And this equation here, you see, is like a Schrödinger-like equation. So it will have some discrete eigenvalue, is a eigenvalue problem basically, with distinct eigenvalues. And this is what is happening. And in case that the effective potential of this Schrödinger-like equation is positive and this C star squared is positive, we can safely say that the black hole is stable. Why? Because we will not have modes, we will not have omega, here, we will not have imaginary omega modes, solutions, in this case, eigenvalues. Because in that case, we can have, if we have imaginary solutions for omega, we can have a black hole that it will basically explode. It will be so unstable, so it will decay, can do whatever. But in case that we have positive effective potential and positive but less than unity C star square, because C star square is related to the propagation speed of gravitational waves. So it should be less than unity. And you see here, for these two figures are correspond to the primary extended Bardeen solution. So close to the horizon, here, close to unity, you see that we have a small deviation in the speed of gravitational waves, but asymptotically, the speed of gravitational waves goes to unity. So very close to the horizon because of the change of the field and because we have this kind of scalar tensor theory, this can change. It's not one-to-one matching with gravitational, the propagation of gravitational waves, but they are related. And the effective potential, you see, it's positive. So actually, we can safely say that actually the solution is stable. So I will not repeat myself again many times, so I can skip the conclusions, but let me mention some future directions of research. So what we did is that we found black holes with primary scalar hair in the context of beyond Horndeski gravity. we studied the axial stability, and what we are trying to do now with Sebastian, Simon, and Karim, we are trying to understand the polar stability. And this is basically the work of Simon. So yes, still we're trying to understand how we can deal with the polar stability of these solutions. Also, very importantly, the quasi-normal modes of these black hole solutions is very, if they are stable, it's very important to study the quasi-normal modes, because quasi-normal modes is a smoking gun that in the future we might be able to observe, and we can distinguish objects that are related and coming from GR, or other compact objects that are solutions from a modified gravitational theory. Very recently, 2 days ago, Konoplia, Stasko, and Stuchlik, they published they published a paper basically only on archive. They uploaded a paper on archive where they study the quasi-normal modes of the first example that I showed you with the solution with arctan. Another question is, can we generalize the method to find black hole solutions that are inhomogeneous? The answer is yes, and this is again what we are doing with Sebastian, Simon, and Karim. And finally, it would be amazing if we could generalize this setup to describe rotating black hole solutions with primary scalar hair, because as you know, any realistic black hole solution is rotating. It has some kind of angular, even small, but it has angular momentum. But our solutions, for simplicity, are all static. Thank you very much for your attention, and I would be very happy to answer to questions. Thank you.
Thank you very much, Lori, for the very nice talk. Are there any questions from the audience? Yeah, Daniel Cruz.
Hello. Sorry, maybe I missed it, but
Yes.
what are the assumptions we impose when we say that the G00 and G11 components are reciprocals of each other? Like, what do we lose by assuming that?
Sorry, it's very. I cannot hear you clearly. Can you repeat, please?
Let me try.
Could you repeat? You said something about the homogeneity, G not not. Sorry? I
Could you
I
repeat?
cannot hear you. I cannot
You're
hear.
muted now.
I'm muted? No.
Not you, Theo.
Okay, okay. Okay.
I th
Okay. It will be typed, I think. The question will be typed.
Yeah. In the meantime,
Yes.
you can ask a question.
Yeah, thank you very much. This has been a really nice talk. And I mean, you addressed it already in the end. The most interesting continuation of this work for me would be look at rotation. So do you have some idea how you might attack this problem?
Not really. We tried, but we failed. But of course, there should be a way. So for other simpler cases and theories, people, I think also Christos Harmousis with Evgeny Babichev, they have some solutions, rotating solutions in beyond Horndeski, but they are stealth care solutions, I think. So basically, they have the Kerr solution inside a new theory, a new setup. In the same way that we have the stealth Schwarzschild solution inside Horndeski. But I think there is no rotating black hole solution with primary scalar here or even secondary scalar here in this context, at least. Because
Yeah.
you know that the equations of motion they become exponentially harder to solve. Maybe AI will help us with this.
Oh, very
Maybe,
nice idea. Yes,
maybe.
maybe. Yeah, yeah. Okay. Thank you very much.
Thank you. Let me see the question.
Yeah, the question is in the chat.
Yeah, okay. Yes. In Proca. Okay.
No,
Okay, let me start.
that's another
Let me
one.
start from the first one. So, for the reciprocal, yes. So, I cannot change. What we are trying. Let me go back. From here, the reciprocal condition, the homogeneous condition, if you may, that we imposed, it was in order to solve the equations of motion in the simplest way possible. Because if we assume that G naught naught times GRR equals minus 1 from here, so basically H is equal to F, then we can immediately solve equation 1 from here for Z equals to gamma, just a constant, and we can easily again solve equation 2 under this assumption. And we solve algebraically the second equation in terms, we solve it for x. And we find the radial expression for the kinetic term of the scalar field. So that was the reason why we did this. But in the paper that we are preparing now with Sebastian, Simon, and Karim, we generalized what we have done here for solutions that are non-homogeneous solutions. And for the second,
Yeah, there is no question for the second. I think Heloise wants to ask something, so yeah.
yes,
please do.
okay.
Yes, but I think that Yu Chen was before me. So
Well,
Okay.
Chenyu is the organizer, so I can ignore him as much as I want. No,
so
no,
yeah,
go
let
ahead,
me
sorry.
thank you for the complete talk. It was very interesting. I was more wondering on the deriving the polar perturbations
Yes,
and why is it so complicated, even in the case of a spherically symmetric background? Because in principle, you have additional contributions from the scalar field, but you can also project it on spherical harmonics and assume a
yes.
sigma
So,
R form. So
yes. So, the easy thing in the axial sector is the fact that the scalar field does not contribute. So you don't have delta phi playing any role in the axial sector because the scalar field and the perturbation of the scalar field transforms evenly under parity. So from the beginning even, the resulting equations will be much simpler. And
yes,
this is the first thing. And also in the even sector, you have more functions that appear in the perturbation. So let me, if I may, I can change. I had it here. I have it here basically. Sorry, this is the paper from Redge and Wheeler. So this is the axial sector. We have again H naught and H1. it's the same in GR, it's in the same type of decomposition in any scalar tensor theory. But you see here that for the even sector, what you have, in our case, you will have the scalar field, but you have H, capital H naught, H1, and K, and H2. So you have the scalar field playing a role, and you have four uh, metric functions, and you have of four uh, a system of four differential equations that you have to solve. And this is much harder to solve in generality for in the context of scalar tensor theories. Basically, it's numerically, yes, you can solve it, but what we are trying to do is we're trying to solve the monopole case where L equals 2. We're trying to solve it analytically and to match it to the axial sector
Mhm.
as it is happened for the GR case.
Okay.
But numerically, of course, one can solve it, I think. Yes.
Okay, good. Thank you.
Thank you.
Chayu?
Okay, question? Excuse me?
Yeah, go ahead.
Yes. Thanks for your a nice demo and very interesting. I appreciate your unified family of scalar hairy black holes that recovers the Bardeen solution as a special case. My concern is the severe fine-tuning required to erase the central singularity, since Penrose's Hawking singularity theory applies generically across all standard GR collapse without any parameter adjustment. What natural physical process for the drive and extra physical black hole to fall exactly on this critical mass scalar pair relation?
So, sorry, but the sound is not great. So the question is about the Bardeen and what is the maximum Q that we can have? Sorry, can you repeat the final part? So it was for the Bardeen?
The question is, what natural physical process would drive an extra physical black hole to fall exactly on this critical mass scalar pair relation?
To have this fixing of Q in terms of the mass to make it regular, you mean?
Yeah.
Yeah, I don't know. This I don't know. Yes, this is a very good question. I don't know this procedure. It might be we were discussing this if we can make it work or no, to be honest. It might be a superradiance process.
Yeah.
But of course, we don't have a clear process to suggest. No, I don't know.
Oh, it's okay. Your
Thank you.
theory is nice. You add extra term with beyond Horndeski. It's very good. I hope that there will some more experimental evidence for your theory. Okay, thank you.
Thank you. Thank you.
Thank you. Chayu?
Yeah, thank you, Theo. I actually have a few questions and some comments. So let me start with the comment. So I just put two links in the chat, and I think this paper is all about the full perturbation theory, black hole perturbation theories in general Horndeski theory with shift-symmetry or by some groups in Japan, like Shinji Tsuchikawa and also Kazumi Takahashi-san. So I think they also include axial perturbation and polar perturbation. So I think you may have a look.
Yes, I will check.
Yeah,
Okay,
yeah,
yes,
yeah.
thank you.
And so the question is, so in your picture of the speed, the propagation speed of axial modes, does it go to zero somewhere or go to negative region somewhere inside the horizon? Because you only show the
Sorry,
region, the
sorry.
propagation speed, c square.
Ah, so here,
Yeah.
here it is everything is calculated in terms of the tortoise coordinate.
So
So
you don't know anything about what happened inside, right?
exactly. So
Okay.
we are always outside the horizon, always outside the horizon, and we go asymptotically, if you
I see,
may.
I see, I see, I see.
Yes, because of course, if you enter the horizon, you cannot clearly say what is happening, right?
Yeah,
And
that's one perspective, of course.
yeah,
So I'm just wondering, for example, if you consider perturbation theory, I mean, for example, usually when those C square, if at some point, even inside the horizon, if at some point they go to negative region, or if they go to zero, that may correspond to like instability, Laplacian instability or strong coupling problems that could also be problematic in general. But yeah, if you only focus
yes.
on the exterior region, then yeah, of course, that's fine.
Let me mention this since you have this question. So Christos, Harmousis, Simon, and Karim,
Yeah.
and I think no, even no, sorry, I think Hugo earlier, a former PhD student of Karim Nui, I think they proved first that in the axial sector, starting from Dost or Horndeski, any in up to quadratic Dost theory, basically,
Mm.
you can always find a particular disformal transformation that will make this C star unity. So there is, you make a redefinition, a new disformal frame that changes this equation, and they brought the equation into the Regge-Wheeler
Mm.
equation. So where C star square is unity. So you know a priori that it will be unity and it will be the GR speed, a good propagation. But you absorb this correction to the effective potential. So
Oh, I
again,
see. I see.
you have to check the effective potential.
I see.
Yes.
And may I ask the next question? So I understand that in the reverse engineering approach in nonlinear exothermic case, you could have problems. So, but I'm actually thinking the possibility of doing reverse engineering in your model. For instance, like for example, the question would be, can you can you reverse engineering starting from any non-singular regular black holes and then with some additional parameter in the metric, but using your reverse engineering and construct the corresponding theory such that your coupling constant, your theory doesn't depend on mass.
Mm.
Do you think that's possible or not in your case?
You can try to play this game. What we try to do, for example, and it didn't work, is we tried to reverse engineer wormhole solutions
Oh,
in our model, and we couldn't do this. And basically, we proved that starting from a black hole solution, you can never create through this formal transformation a wormhole solution. In this case, you can never create a wormhole through this formal transformation of a black hole in this setup, because there are different setups that you can do this. Uh, so we try to do and to reverse engineer wormholes, but we didn't manage to succeed. Maybe
I
there
see.
is a way. Maybe there is a way, and maybe there is a way even for other types of black hole solutions.
I see. Yeah, I actually have a last question, but if if there are other people wants to ask other questions, maybe.
Does anyone else want to ask a question? No, go ahead, Chayu.
All right. So I'm actually thinking maybe it's a still bit of crazy idea. So I understand that if you have a shift symmetry, you can put a scalar chart QT in your scalar field profile. But do you think that why don't people consider the possibility of adding something in the azimuthal angle? So
They
for
did.
example, some constant times phi, which
Yes,
in principle you can do that, right?
they did. I think, to be honest, I have done the computation.
Oh,
You are not allowed to do it with the theta angular component, or uh, so you can do this only with one of the two angles. You cannot do it with both. I think there are papers doing this for rotating, and even for the stealth care solution. I think they have this, but I'm not 100% sure.
all right.
But people tried to do this.
I see. Yeah, there must be a reason why
Yes,
I
I think
mean, people don't really consider that in the
I
past.
have done the computation some years ago. Uh, I think you are allowed to do it with one of the two angles.
Okay.
The other one does not behave properly, because in that case you generate angular dependence in your solution. You want to generate this for axial symmetric, but you don't want to break the properties like the parity. So I have to check again, and I
Mm.
can uh, I can contact you
Yeah,
later.
sure.
Yes.
I'm actually mainly focusing on phi. I don't care about theta. I think there would be problem if you
Yeah.
add something
With
corresponding to
phi,
theta, but phi, yeah, for
yes,
phi it could be possible.
I think it is possible
Okay.
up to an extent. Yes.
Okay. Thank you. Yeah, I don't have other questions. Very nice talk.
Nice. Uh, well, yeah, I actually have a small question, but you might have mentioned it. But so there are I think there are these constraints by Takahashi, Motohashi, and others about the even modes in the host stealth here, right? I don't know if you
Yes.
mentioned it.
Yes. No, I haven't. Yeah.
So how do you think has anyone seen this in your theory? How are you going to avoid these yeah constraints on gradient instabilities, for example, as they show? Because the result I think is in generic dehost. So I don't know if your theory is a subclass of that. So yeah.
So I don't. Okay. I don't remember the paper by heart, but I know, for example, for the stealth solutions, uh, people have shown, and they have proved explicitly, even asymptotically, I mean, close to the horizon and at infinity, they have shown that they are strongly coupled in
Mm.
this theories in Horndeski, I think. Uh, I'm not. I think nobody showed this for our solutions. Maybe there is a problem. I cannot say there is no problem. We are trying to solve the monopole sector for L equals 0 for the polar. We have results that we solve this analytically, and it's okay. And
Yeah.
this is okay. In general, generically, I cannot say anything about the polar sector, but I will check uh, again this paper that you mentioned. Yeah. So
Good.
you say that they have general results about those theories?
Yes, I think so. So I think they prove that even modes are all dangerous somehow. So yeah, they
Okay.
create gradient instabilities.
Yeah,
I
maybe
know
this
that
is the
there are
case.
some other constraints by, I don't remember the names, maybe Noller and someone else. They have found some stability constraints about the parameter space of M and Q based on the odd parity perturbations. But I think that Takahashi and Motohashi, they have some generic result in the host theories that they say basically that all even modes are dangerous and potentially lead to gradient instabilities. So,
Okay,
yeah.
I need to check this again. I need to check this again.
Yeah.
Takahashi is one of the authors of the papers that I put in the chat. Yeah.
Good.
So
That's what
maybe,
reminded me of the
so they may be cited somewhere in the paper, or they are.
Okay.
Could be. Yeah. Great. Okay, let me stop the recording then.